Okay, and hi everyone. Thank you so much for joining us for the fourth session of the day on JNation Online 2021. So I'm very happy to have with me Jose and Maurice. Hi Jose, hi Maurice. How's it going?
Hi, Roberto.
So Jose, you're in France, Maurice, you're in Scotland, right? I'm guessing that both of you are following the Euro Cup. Or you guys don't really like football?
No, not at all.
Just Java, right?
When are we going to beat you, Roberto, again?
Other things, but not football.
Is it tonight or tomorrow night?
It's gonna be like in a couple of days, right? So hopefully, let's see what happens. But yeah, it's gonna be fun. Yeah. So anyway, Jose and Maurice are gonna bring us a really cool session that I already have the chance to have a look at. So I guess that without any further delay, let's go for it, right?
Sure. Hello, and welcome to our talk on the sincerest form of flattery and to JNation. We hope you're enjoying the conference. According to the English proverb, the sincerest form of flattery is supposed to be imitation. And this talk is about how mainstream programming languages, Java and Scala in particular, have been gradually accumulating and imitating the best features of functional languages. It's not been a completely straightforward process, and we're going to describe some of the problems Java and Scala have met along the road and how those problems have influenced the shape that functional features have taken in those languages. Our hope for this talk is that at the end of it, as Java programmers, you'll have a better understanding of why things are done the way they are in Java and an appreciation of new functional language features that are continuing to appear in Java. If you're a Scala programmer, you can just look on and feel smug. Well, most of the time. So I'm Maurice Naftalin. I've written about Java 5 and about Java 8. I'm putting those books up on the slide because they're actually useful references for a lot of the material we're going to be talking about today. I'm a member of various community programs, including the Java Champion program, and I have been a rock star speaker at Java 1 and Oracle 1. And this is José.
Thanks, Maurice. My name is José. I'm very glad also to welcome you to this talk. I just joined the Java platform group at Oracle just several weeks ago as a Java advocate after spending about 25 years working at the university here in Paris. So here are just some links with the content I have published over the years on the internet, on GitHub, SlideShare, YouTube, and other places. We are currently recording this session. Maurice is in Edinburgh. I live near Paris. We are doing this talk for JNation in Coimbra in Portugal. We have been doing many things online lately. This is how it is. So hopefully we will be able to organize in-person conferences again as near in the future as possible. And by the way, I'm also a Java champion and a Java 1 workstar and a member of the Paris Java user group. And I'm also, and I'm quite surprised, Maurice, that you didn't mention that, but I'm also the disorganizer of J Chateau, an unconference that shamelessly copied J Alba that you created several years ago.
But you know, imitation is the sincerest form of flattery.
Absolutely, absolutely. And this is really the core of what we're going to talk about now.
I'm really hoping that J Alba is going to be something very real again soon. We're still talking about doing a virtual J Alba this year, but a real J Alba next year is something to look forward to.
Absolutely.
So what's this all about? Well, functional programming has been around for pretty much as long as there's been programming. Or almost as long. And computing scientists have always really liked functional programming languages. They're elegant, they're mathematically sound, it's easy to prove the properties of them, and it's easy to convey complex ideas in them in a clear way. The key elements of functional programming languages have been present for a long time. They came in progressively. Higher order functions, which we know as lambdas in Java, came in the 1950s.
parametric polymorphism, which we know as generics, came in the 1970s, and pattern matching, which we're just getting to know, came in the 1980s. These have been around for a long time and are well-established ideas in programming. But for all that, functional languages have never really become widely popular in the commercial environment. And the reason for that is mainly because functional programs tend to be quite inefficient without a great deal of care on the part of the programmer. They're liable to be expensive both in terms of execution time and memory. Object-oriented languages, by contrast, have been very successful. They certainly can be made very efficient, and they do have very positive features of their own. So object orientation brings with it subtype polymorphism, which we know as inheritance, strong static typing, which has been a big feature of Java from the very start, and automatic memory management, which is a huge aid to programmer productivity. But for all that, object-oriented languages have always suffered from feature envy when they look at functional languages. Here's our picture of functional languages besides object-oriented ones. So very early on in the evolution of Java, in 1997, when Java was really still a very new language, my friend Phil Wadler, and the bearded guy on the right of this picture, he's a very well-known functional programming academic. He was told by a student of his that he should pay attention to a wizzy new language called Java. And together with Martin Odersky, who's in the picture on the left, he's the man who went on to develop Scala, they created a proof of concept language called Pizza, which showed how, in principle, it would be possible to add these three features of functional programming languages into the newborn Java. Sun Microsystems adopted the polymorphism element of Pizza and sponsored Odersky and Wadler, in collaboration with another two contributors from Sun, in creating another proof of concept language called generic Java. The breakthrough idea of generic Java was how to handle the backward compatibility problems that we're going to be talking about today. But those were big problems, and they frustrated Odersky so much, and the solutions contained so much compromise, that he decided to go off and start from scratch with a totally new language, Scala, which was launched in 2003. The difficulty of getting generics into Java because of these backward compatibility problems meant that it wasn't until 2004, a year later, that generics actually appeared in Java 5. So Scala was able to eat pizza, the three features of functional languages, in one bite: generics, closures, and pattern matching, all in one go. But Java, by contrast, has taken three attempts to incorporate the ideas of Pizza. Parametric polymorphism, that's generics, in 2004, higher order functions or lambdas in 2014, and pattern matching in 2000 and, well, real soon now, right?
Real soon, hopefully.
Yeah. So José will be talking about that a lot later on. So let's have a look at each one of these features in a little more detail. Java generics is the one that has suffered most from the problem of backward compatibility. The biggest single problem that the designers of generic Java faced was that they knew that during migration from non-generified or legacy types to generified types, there were going to be incompatibilities between library and client code. Library code would change at some point from using raw types, that is non-generified ones, to using generified ones. So here we're imagining a library method which is going to return a list of string. But prior to generics, it can only return a raw list without any generic type information. And the client code that is calling that also has to make a corresponding change in going from expecting to get a raw list to expecting to get a generified list of string. The problem about this migration is that these two changes in the client and the library can't be guaranteed to take place at the same time. And you don't even know what order they're going to take place in. So any combination of either of the variants of the client code with either of the variants of the library code is possible. And all four of the combinations have to work for migration to be successful. But migration was successful. So moving Java to generified types was a huge achievement. So in talking about the problems, which I'm going to do now, of how they dealt with it and the difficulties that creates, I don't want to suggest that this was a mistake. Type erasure, which I'm going to talk about now, was necessary in order for migration to succeed, and therefore in order for Java to remain in the forefront of programming languages. So all four combinations had to work. And what that meant was that for binary compatibility, the runtime representation of a raw list had to be the same as the runtime representation of a list of a list of string in this case. And since there is no runtime representation of the generic type of a raw list, it doesn't have one, so there's nothing to represent. What that meant was that there could be no runtime representation of the generic type of a list of string either. It had to be erased at runtime. And that was a solution adopted by the generic Java designers. With type erasure, the generic types that are known at compile time and used by the compiler to do strict type checking, that generic type information is discarded and does not persist at runtime. So you get all of the advantages of generic types in terms of ensuring that in terms of ensuring type correctness, and assistance from the compiler in terms of automatic type inference. But the drawback is you don't get to use them at runtime, and that has some unpleasant consequences. One consequence is that you can't do a runtime test like instance of on a parametric type. So here, the type of the parameter param is a generic type T, and in this example, we would like to ask it at runtime, is it of type string? But we can't ask that question at runtime because the type T has disappeared. It's been erased. An even stranger drawback is that you can't create arrays of generic types. In general, we're going to see that the typing scheme for arrays is not really compatible with the typing scheme for generics. And this is one particular way in which it isn't. Arrays, unlike generics, do know their component type at runtime. It's actually baked into the definition of the array. So in this case, the red code there is trying to make an array of a type, list of integer, which can't exist at runtime, as I've just explained. So you can't have an array of it, and that code therefore is illegal. The variable declaration on the left is perfectly legal. You just can't give that variable an appropriate value. How irritating is that? And that brings me on to the second big problem of backward compatibility with generics. And that is the way that variance is implemented in arrays compared to the way it was implemented in generics. What's that about? Well, from the start, Java needed generic methods. It had to be possible to write methods like this one from the utility class Java util arrays that would be able to work with different kinds of objects. A language that couldn't support generic sort methods would have had no plausibility at all. The same algorithm has to be usable for arrays of integer as for arrays of string. But for both of those calls to sort, for them both to work, the type of the variable ints on the left must be a subtype of the object array type that sort is expecting, and similarly for the array of string on the right. So integer array and string array must be subtypes of object array. This is called covariant typing because the type of the array varies in the same way as the type of the components. Because integer is a subtype of object, integer array is a subtype of object array. So to make generic methods work, covariant typing was the type scheme that was adopted for arrays, and this works sort of okay. It's got some drawbacks, which we lived with for many years and never thought anything of. One consequence of it is what we're showing here. We're creating an array of integer, assigning a reference to that array of integer to a variable of type number array. Then we're retrieving an element from that number array and assigning it to a variable of type number. And that works fine because, and this is an important point, covariantly typed containers are good for retrieving values from. Unfortunately, they're not so good for putting values into, as you see with the red code on this line. Although it's statically well typed, because a double is indeed a subtype of number, so it should work. But remember that arrays know their component type at runtime, and this one knows that it's not an array of double. So what should be a compile time error becomes instead a runtime exception. Now, this is an unhappy situation, and they didn't want to reproduce it for generics. So they adopted a different scheme, invariant typing. A list of integer is not a subtype of a list of number, as with covariant typing. In fact, it has no direct relation to a list of number at all. And that's great because we don't get the problem that I just showed. But wait a moment. This problem arose because we actually really did need covariant typing for generic methods. Like this one in Java util collections, which works on a list of any reference type, just like the sort method on arrays. That method works on types that know how to compare themselves because they implement Java lang comparable. But comparable is an interface, and we can't provide a list of comparable as the precise type of the parameter to sort, because there are no objects of that precise type. It's an interface. What we want is to be able to sort things that are subtypes of comparable that implement it. So for situations like this, generic Java provided bounded types. Here, the extends keyword is used to specify an unknown type about which all we know is that it is a subtype of comparable. Now, a list of T extends comparable is indeed a subtype of list of comparable. So we've got covariance back again. And a bonus from this idea is that it leads naturally to the opposite notion of contravariance, where covariance has the type of the container varying along with the type of its component. With contravariance, the type of the container varies in the opposite direction, so that list of T super number is a supertype of list of number. And that's useful because in the same way that covariantly typed containers are good for getting values out, contravariant ones are good for putting values into. And here, to demonstrate that, we've got a little append method which takes values from a covariantly defined source list and puts them into a contravariantly defined destination list. In the body of the loop, each element is retrieved in turn from the covariantly defined container and put into the contravariantly defined destination. So that method can be called to append a list of integer to a list of number. And we've not only recovered generic methods, but done something that wouldn't have been possible with the less flexible covariant only typing scheme of arrays. So that's Java's way of implementing variance. How does Scala handle variance? Now there was a big opportunity there for the designers of Scala, because it was a new language free of the constraints and the backward compatibility problems of Java. They could start off not only with a new language and a new type system, but also with a new collections library. So they could take advantage of something that had become much more fashionable in programming between the design of Java and the design of Scala, namely the idea that immutability is a very desirable characteristic of containers, or at least of some containers. By the way, this idea of the desirability of how desirable immutability is also came originally from observing how much nicer functional programs could be when they could rely on the immutability of their containers. So the Scala collection classes include ones that are immutable by declaration, something that's very difficult to do in Java. I mean, defining immutability in Java is quite hard, but in Scala it's really easy, because if you define variance at the time that the type is declared, rather than when it is used as Java does, you can declare a container to be covariantly typed, and the compiler will ensure that you will never even try to assign an element to it. So here's a pair class written in Java that takes a type parameter t with in Scala, that takes a type parameter t with the plus sign there, indicating that that t is to be treated as a covariant type, with the result that the container is, by definition, covariantly typed. If you want to do the same thing in Java, you can still define a pair class, but you can't say what the type of t, what the variance of the type of t is in that definition. And therefore, when you want to make a call on it, as in this case, we've got a toString method, which is going to take the elements out of the pair. In other words, require the pair to behave covariantly. The type parameter to pair that we have to use is this question mark, which is actually a shorthand for t extends object. This is the client programmer using that library class, having to say, I want this class to be treated as a covariantly typed container at this point. Whereas in Scala, by contrast, if you wanted to do the same thing, you can simply define your toString method, or the library designer the designer of the pair class can define the toString method on a pair of any val, which is the top of Scala's type hierarchy, the equivalent of Java lang object. So the work of handling variance, whether covariance or contravariance, has been taken away from the client programmer and given to the library writer instead. Well, I mean, that's what library writers should be doing for a living. They should be doing the hard work and making things easy for client coders. Isn't that right? I'm a client coder, so I would think that.
Well, I guess I'm a client coder too, so I'm fine with it.
Well, one thing that we can agree on, whether we're client or library coders, one thing we can agree on is if there's hard work to be done and it can be done just once rather than having it to be done over and over again, the right place to do that hard and difficult work is in the library, because that's a place where you can concentrate on the difficulty and focus it and do it once and make life easier for all the client programmers who'll come after. In fact, there's a proposal somewhere in the Java development pipeline, I'm not sure where, for this declaration site variance, so-called. The variance is declared at the site of the declaration. That's what Scala has. There's a proposal for that to be introduced into Java as well. So that concludes our very brief survey of the introduction of generics, and it shows above all the advantage of starting from scratch with a language which could use the experience of the generic Java design and could be defined without backward compatibility constraints. There are two sides to this coin. Scala has used this freedom very liberally and has continued evolving without much emphasis on backward compatibility. So you can't have the same confidence that legacy Scala programs will run on new language versions as you can with Java. And we'll talk a bit about that at the end. There's different design philosophies have gone into the two languages, and both of them have their advantages and both have their disadvantages. So generics was the first part of what we're going to talk about. Part two is closures and lambdas. What Pizza did for closures was to try to solve the question about how functions could be introduced into a language which didn't have them in the type system, unlike functional languages, which are designed to have functions as as first-class citizens, fully qualified objects, fully qualified values at the highest level. But Java didn't have this. Java has a type system of an object-oriented language without functions as an idea that's independent of classes and interfaces. Classes and interfaces, not functions, are the fundamental things in Java. Well, so they had a choice. They could have rewritten the type system to include functions, but that would have been a very big revision. Their solution instead was for each function to be created in an abstract class. In other words, fitting into the existing type system, and to use these abstract classes as a wrapper, in a sense, for a single apply method, which would be the real implementation of the function. Functions in Pizza, functions look like first-class citizens, just as in an ordinary functional language. The syntax is like this. Here we have a max method, which takes a list of s and a function from two s's to Boolean, and max is one particular method which accepts a function. It applies that function pairwise to the elements of the list, comparing them to eventually find the greatest, as defined by the supplied function. So you could call max with a different function. The call that you see here is using a function that compares strings for length. So max will return the longest in its supplied list of strings. But it's easy to imagine a different comparator function. Say one that returned a Boolean according to what the order was in the alphabetic ordering. And these functions would simply be parameters to max. So the function there is neatly wrapped up in the syntax of the language, and functions like that can be passed around as parameters. They can be assigned to variables and generally treated as first-class citizens like other kinds of values. And this has been the ideal in functional languages ever since the first functional languages like Lisp were invented in the 1950s. When they introduced lambdas into Java in 2006, the debate over whether to follow Pizza, this kind of cosmetic model, or to introduce a separate function type, was a very intense debate. And that was something among the many things that held up the introduction of lambdas into Java for a long time. That was a major cause. It was eventually resolved a long time later, prior to just before lambdas were actually introduced in 2014, in favor of the pizza solution. We use a single abstract method within, well, not within an abstract class as pizza suggested, but within an interface. Functional interfaces as we now know them. In effect, these are wrappers for the function that is implemented by the single abstract method, however it's named, of a functional interface. And this hack meant that there was no change needed in the type system. Now, I call it a hack, but it's quite an elegant hack. And it's got a big payoff because it allowed functions to be introduced into the language without a massive upheaval. And it worked very well from that point of view. So Java 8 and lambdas was one of the biggest successes that Java has had. So finally, pizza left open one important question that was resolved by Java and Scala, but in different ways. This question was, should functions be allowed to capture and use non-final local variables? Final local variables are really just fixed values, so using those isn't controversial. If you allow non-final local variables, a closure will carry a reference to its environment around with itself. And it can access local variables long after the executing thread has exited the block or method in which the variable was defined. So you'd think the local variable doesn't exist any longer, but this closure still has a handle on it. In fact, since functions can be passed between threads, this can easily result in different threads executing the same function and so simultaneously accessing the same local variable. Now, should this be allowed? The pizza designers sat on the fence on this question. There are attractions to doing it. But Java said no, because Java programmers have always relied on thread safety of local variables. Scala said yes. They wanted the flexibility and power of what are generally called closures to distinguish them from lambdas. JavaScript programmers enjoy the same feature, or maybe they endure it, because it makes programs much more difficult to understand and to debug. So closures in Scala can capture vars. And if you're worried about the thread safety of the resulting code, well, you're on your own. This is one design decision where, personally, I strongly side with Java. And I think you feel pretty strongly about this as well, don't you, José?
Yes, absolutely. I think that having concurrent access on local variables, well, not having that in Java is really a great relief.
Yeah. It really was a no-brainer from the point of view of backward compatibility. All kinds of programs which were thread safe and would work perfectly even when they were run on many threads would have stopped working under these circumstances. It really wasn't something that Java could consider. We're on to our third part. That's the section on closures and on lambdas. Compare them.
Absolutely, because the last part that is still missing in everything that Java could steal from Scala and Pizza and all these languages is pattern matching. And the pattern matching is really something completely new for the Java developers, and it's something that is coming in the language step by step, as we're going to see. And I think it's really great. Pattern matching is in fact the next major feature that will be added to the Java language. It's a language feature that will bring new ways of solving problems using the Java language, and it's really great. As you know, Java has now a major version every 6 months, meaning that a feature is now delivered step by step, and this is the case for pattern matching. Instead of having one major release with one massive update of the language, of the JVM, of hundreds if not thousands of classes across the JDK, by the way, that was the case for Java 8, we now have small steps with one thing at a time. And this is what is happening for pattern matching. As we saw, pattern matching is not a new idea. There was already support for pattern matching in Pizza, as you can see it on this example. Here you have two sealed classes. Well, we have one sealed class for Pizza, a vehicle class with two extensions, car and bus. And the Pizza language knows that there are no other extensions allowed. So you can see that a car is constructed on a color that will allow for deconstruction. More on that in a minute. And you can switch on types, and you can use deconstruction as long as you know how the type was constructed precisely. And the same goes for Scala. In fact, the syntax in Scala looks like the one you have in Pizza. Here we have sealed classes, then a switch on types that can also leverage deconstruction to create variables. The switch we have here can be an exhaustive switch without the need for a default clause because the type is sealed. And this is something that is coming in Java too. In Java, pattern matching is developed under the umbrella of the Amber project. We already saw a first piece of pattern matching with the pattern matching for instance of that was released as a feature in Java 16. What you can do with this pattern matching is write this kind of code. If O is an instance of string, and then you can add a variable S that is created in case O is indeed a string. Then you can use S wherever it makes sense. So in that case, it is the first branch of the if statement, but it could also be used within a Boolean expression within the if statement argument, if this is what you need. What is a pattern? And to be very precise, I would like to quote Brian Gertz, the Java language architect at Oracle. A pattern is a combination of a match predicate that determines if the pattern matches a target, along with a set of pattern variables that are conditionally extracted if the pattern matches the target. So if we go back to the previous example, here we have string, name, and this is the type pattern defined on type. String is the name of the pattern. Name is the pattern binding variable that is created if the pattern is matched. And O is, of course, the target operand. So we can add patterns to the current switch expression added to Java AC14, which is currently being worked on. So we will have that in the future. Here is an example of what we could have. Here we have three patterns, integer, long, and double. We have three patterns binding variable, I, L, and D, and one target operand, which is the argument of the switch expression, number. Java 16 saw the addition of another feature from the Amber project called record. A record is defined on components, declared along with the record itself. The compiler will generate many things for you, including the accessors, which are not getters, by the way, as we can sometimes read it, along with the equals method, the hashcode method, and also the toString method. Now, you can wonder how our records are related to pattern matching. Well, in fact, you saw deconstruction pattern in Pizza and Scala, and record are just the perfect concept to handle deconstruction. So, to declare record, you just need to write that. Public or not, record, car, this is the name of the record, and then color, and color is just the component of this record. Or you could write public record rectangle, int width and int 8, which are the two components of the rectangle record. And by the way, records are also immutable. So you can see that a record is constructed on this component, meaning that you can use this construction pattern to deconstruct a record very easily. So type pattern matching can leverage that to deconstruct a record, just as you saw with Scala and Pizza. So it could give you the following code: O instances of rectangle, then just the component of the rectangle, and here you do not have the choice because it's just two int. You cannot have several sets of different components for the same record, width and 8. And now you have two pattern binding variables, width and 8, that you can use in the right context, which is really nice. It can also be done on switch because it is used, in fact, the same type pattern that is used. So to compute the surface of a shape, for instance, you could be writing the following: switch on the shape, and the shape could be a rectangle, a square, or a circle. So here we have a switch on types. But the type is not, in fact, really a type, but it's a complete pattern matching along with binding variables. So for rectangle, it is width and 8, And then you can use those variables to compute the area, which is going to be width times 8, of course. And the same for the edge for a square and the radius for the circle. So the project Amber also delivered sealed classes as a second preview in Java 16, and those sealed classes are still, as of this recording, a proposed feature for Java 17. So we may have sealed classes as a feature in Java 17. In a nutshell, a sealed type, just as in Pizza and Scala, is a type that can restrict its extensions or implementations. So in this example, we have a sealed interface called shape, and this shape declares two implementations that are final classes, rectangle and square, and a record, which under the hood is a final class called circle. So by writing this code, we know that we can only have three implementations of this shape interface: rectangle, square, and circle. So in fact, all the shape hierarchy is there. It is checked by the compiler at compile time and enforced by the virtual machine at runtime. You cannot add elements to this hierarchy at runtime by using reflection agents or this kind of trick. Using that, you will be able to create exhaustive switch on types without the need of a useless default clause. And by the way, you can already have exhaustive switch expressions on enumerations, for instance. So it's not new for the switch expression. What is new is that you will be able to do that on types using this sealed type feature. There are some nice syntax features also in type pattern matching and deconstruction. So for instance, you can use var to avoid the typing of complex type. If you do not plan to use binding variable, you can use the underscore to tell that to the compiler, and then this variable will not be created, and it will not be bound. All these are in the plans, so hopefully we'll have that one day. You can also nest patterns, which is very useful. So instead of having to write if shape instance of circle, and then you deconstruct with the center and the radius of the circle, to discover that this center is in fact a point, and in fact you're interested in the coordinates of this point, so you have a second instance of to deconstruct the center to a point of x and y. You can nest those two patterns one into the other with the following syntax: shape instance of circle of point of x and y and var radius. And now all those are binding variables. There is also a plan to allow for method deconstruction. So far, we just saw deconstruction on records, and this is quite restrictive because not all your classes can be made records in the future. So what is method deconstruction? In fact, there are many places in applications where you prefer to use factory methods to construct your object rather than using the constructor. This is the case on this example of the shape interface, which provides two factory methods to create instances of circle and square. Well, it could be very useful to be able to use this method to deconstruct a circle and a square, and to be able to write this kind of code: switch on shape. If shape is a seal type, then you know that there is only circle and square as implementation. And instead of using instance of, using this kind of syntax, shape.yourFactory method, circle, double radius, and this could be used as a deconstructor with a radius as a binding variable to this kind of pattern. And the same for the shape.square factory method. That would be really nice, and this is possible that we'll be seeing this kind of pattern in the future. And it could go even further by making it possible to write deconstructors directly in classes along with constructors. That could give this kind of pattern. Suppose you have a class point with a constructor that takes an x and a y, two integers, a very classical point class, and then you could add a kind of the thing that looks like a constructor but that is not a constructor. And it also looks like a method, but it's not a method neither. It's really a deconstructor. Well, it looks like the block of arguments is in fact the output of the method. In fact, this deconstructor and this block int x, int y is really what is going to be deconstructed. It has to match the signature of the corresponding constructor and will be used by the deconstruction mechanism to deconstruct point object. So within this deconstructor, what really you have, it looks like you are copying this .x in what looks like to be the argument of the method. But in fact, this block of argument is not a block of argument. It really is the output of this deconstructor, because this is neither a method, neither a constructor. This is really a new concept in classes. That could support overload. So if you have multiple constructors, you could also have multiple deconstructors associated to them. That should be really nice to have this kind of feature also. So we talked about type patterns, but they are not the only pattern one can think of. For instance, you can also think about the destructuring pattern using a new concept and probably a new keyword also, match concept, that could lead to very interesting things. Let us see that with a new keyword that does not exist, of course, which is the match keyword. So for instance, if circle is a record, writing this code, match circle of var center var radius equals circle would create a center and a radius binding variables that you can use later in your code. Now, what could happen if this circle variable does not match this circle? Well, you have a problem because nothing is defined, but the syntax could be extended with, for instance, an else clause that in that case here would throw an illegal state exception in case shape is not a circle. But instead of throwing an illegal state exception, you could also define default values for your binding variables. And by the way, this way of setting the binding variables by hand, let us call it in that way, is called an anonymous matcher. In fact, this else clause is an anonymous matcher that can match your binding variables without having any record, any circle record defined. And now that you have that, really all these elements makes it such that the sky is the limit. You can also match more than one element in a single match. You can create as many binding variables as you wish. So you can write this kind of code, switch, and you have this rectangle that is a shape, and you extract P1 and P2 that are the component of the rectangle. But in the same round, you can also match P1 to a point and then extract the components of this point, the coordinates of this point. And if you have a second point, you can also do that with a second point. This pattern can also be nested, and you can see that there is really no limit at what you can do with this kind of pattern of code. But you could also go one step further and decide to destructure collections and maps, because since Java 9, I think I remember, we have those convenience factory method for collections and maps. So we can create maps and collections with factory methods. So if you are able to deconstruct elements with factory methods, it means that you can also deconstruct a map or a collection with those factory methods. So you could write this kind of code, map instance of map with mapping, and suppose we have that, and then pass a special value for the key and decide to bind the value that is bound to that key in a binding variable. Instead of checking if map is a map, if there is a key that is called name, and then extracting the key, all this can be done in just one line of code with pattern matching. And if you need to get the email of the person also, you can do that by also checking if there is an email key in this map. By the way, this AND operator is the classical AND Boolean operator that you can use in an if statement. But it means that you have two pattern matching. The first one will be evaluated, and then the second one if the first one is true. But you could also do that in just one pass with a single pattern matching by adding a special operator to realize, to execute AND Boolean operation among pattern matchings. So just to show that, we can use this keyword underscore AND, which is a Boolean expression, but not between classical Boolean values or Boolean expressions in a language, directly between pattern matching. So this is in fact a new operator of pattern matching. And so now you have just a single pattern matching, which is the combination with this AND Boolean operation of two simple pattern matching, extracting the two binding variables, name and email, just in one pass. which is absolutely great. And you could go even further if you need to analyze a JSON file, for instance, that can also be created using factory method with a string key, int key, object key, this kind of thing, factory method. All you need to do is just create one pattern, JSON, instance of, and then create one pattern with all the combination that you need and extract all the elements of your JSON file using this binding variable mechanism. It's just one line of code, it's just one expression to evaluate, and it's super powerful to be able to write this kind of code. On this example, the JSON file is really tested in one pass with this pattern. It makes your code less error-prone, it makes it much more reliable, much more robust. I really love it, and probably also much more performant, which is also really great. One last example, suppose one day, we can still dream about that, Java gets maps literal, meaning that you will be able to create a map with this kind of pattern. Here we have the key value pairs directly written between curly braces. Well, if you have that, you could imagine also some pattern matching with binding variables in this kind of pattern. So having map instance of, and just between curly braces, right? Okay, if there is a key, first name, then bind the value bound to that key in this binding variable. Same for last name and same for age. And by the way, on this pattern, if you have a key now, you can see that there is a nested pattern because the value of the map, which is a string, can also be pattern matched, let me call it like in that way, with this integer.valueOf, which is another factory method of the integer wrapper class, just to deconstruct the age on which this string has been created. So this is really great. This is the kind of pattern that could be added to the Java language in the future with the Ember project. All right, so to wrap up this part on the pattern matching, there is a bunch of patterns that can be added to the language. We saw the constant pattern, we saw the type pattern, and we have already a piece of the type pattern with pattern matching, for instance, of. We saw the deconstruction pattern. We saw that they can be nested, they can be defined on constructors, they can be defined on factory methods, and they could be defined on literals if one day we have literals in the Java language. You have the method patterns, the var patterns that rely on type inference, and the any patterns that uses the underscore. You can use patterns in several places. We already have the instance of place, which is a predicate, and this one is already available in the current JDK. You could have it in a switch statement or expression, and this should be a preview feature in the JDK 17, so next release of Java in September. It could be done in a match statement, and this is not done, this is new, maybe we'll have that in the future, or in a structure pattern to work with map, with JSON objects, with literals, with lists, with arrays, and probably some other structures as well. And that's it for the pattern matching, Maurice. That's a lot of project to come in the Java. I hope you are as excited as I am with all those new features.
Yeah, it's really impressive. It's really impressive, the scope of this.
Yeah, absolutely.
So, in conclusion, we hope this talk has been satisfying, both in the sense of looking backwards to understand what happened in the past, and also to look forward to anticipate the features that are going to be arriving soon. Clearly very exciting. In this talk you've had basically past with generics, present with lambdas and closures, and future with this great world of pattern matching that José has been describing. The conclusion that we can draw from this whole thing is that language design is a really, really complicated business, and never more so than when your changes have to be compatible with 2 decades of previous development, not to mention the next 2 decades of future development. In doing that, you're traversing a very complex, multi-dimensional design space. Java takes it very seriously because Java places a very high value on backwards compatibility. You could still run in modern versions of Java code that was written 20 and 25 years ago. So, as I mentioned, Scala made a different decision. The designers decided there that fast language evolution was more important than backward compatibility, with the result that the language has been very dynamic, but hasn't been very stable. It's evolved very quickly, but each release of Scala has brought its own compatibility problems. So each viewpoint has its advantages, and both have their disadvantages as well. The development of Java now is guided by the chief language architect, Brian Getz. And José has a favorite quote from Brian to explain why Java evolves in the way that it does.
Yes, Brian once said that we don't want to be the first to include a feature because every feature we add will never be removed. It will stay forever. And we both know, Maurice, that forever may be a very, very long time indeed.
Indeed, indeed. So thank you for your attention. I hope you've enjoyed the talk. There's a question and answer session now, and we're very happy to talk about it. And I hope you enjoy the rest of the conference. Bye.
Bye.
Okay, and so that concludes our session with José and Maurice. So that was a great session. Thank you so much for bringing that to us. I believe we have a question from the audience. So Ambu is actually asking, where can he learn or read even more about the Java pattern matching?
So I'll provide you with links. There are several links with documentations. Since this is still a set of features that are not being published for the biggest part, there are several links of documentation, like I would say white papers and this kind of thing that you can read on the subject, and I will give you the links. And we'll put that on in the description of the YouTube video, I suggest.
Okay, wonderful. And I'm pretty much guess that we are out of time. So again, thank you, José and Maurice, for bringing us this session. And hopefully we can see each other again really soon in person. Okay, so we're gonna do like a really quick break. So take some time to get some water, some coffee, and we're gonna resume in roughly 9 minutes. So see you soon.
Thank you very much.
See you soon. Thank you very much.